CRT recycling technologies. It's my pleasure today to introduce Allison Schumacher, who will be our moderator. Allison Schumacher is the Senior Manager of Environmental Policy and Sustainability of the Consumer Electronics Association. She worked on federal and state electronics recycling and energy efficient policy and oversaw the wonderful contest you're about to hear more about. Give a warm welcome for Allison.
Thank you to Bobby and to Jerry and the whole staff at Resource Recycling. We're really happy to be here and to talk first with our previous winners of the Cathode Ray Tube Challenge and then learn more about the winners for the 2013 competition. I'm going to start just with a couple of slides that I put together to give you background on what CEA is doing in this space. Our membership is comprised of all the major manufacturers and retailers, and we've got more than 2,000 companies that work with us on a variety of policy issues. As Bobby mentioned, I work on environmental policy at the federal and state level, but we cover all different policy angles in Washington and in all the different state capitals. We work a lot on e-waste issues. We work very closely with our partners at the ERCC with Jason Linnell and his fine group and the National Center for Electronics Recycling. We also work very closely with all the different state agencies and the regulators in trying to make sure that e-waste is being recycled properly and that we're doing it in an economically efficient manner. It's a very high priority for our companies, and it takes a lot of work, and we're making good strides on these issues. One of our major policy initiatives that we're happy to talk about is the E-Cycling Leadership Initiative, and we launched this about 2 years ago. It's the first industry-wide program, and it's also nationwide. And we have challenged ourselves to recycle 1 billion pounds of electronics nationally by the year 2016. So we're counting consumer pounds from both the mandatory state programs as well as voluntary programs. In terms of success, we are doing a great job, I think, in terms of raising awareness among the public on where to take old used electronics. One of our major focal points there is a website that we have called Greener Gadgets. It's www.greenergadgets.org, and it has a fantastic zip code locator in there where in just a couple of seconds you can type in your zip code, pull up the closest locations to you, and find hours, days, types of electronics recycled. And we're trying to make it as easy to recycle as it is to purchase the electronics. This past April, we announced the results of our most recent progress report, and we recycled more than 585 million pounds of consumer electronics in 2012. That's up 27% from the previous year, and up a full 95% from the start of our initiative based on numbers from 2010. We still have a lot of challenges, particularly when it comes to CRTs. We have been active in this arena in a bunch of different ways. We have worked together with other stakeholders on trying to understand the market flows a little bit better, and we've also tried to do some of these innovation contests to see if we can look outside the box of industry and find other innovative ideas out there that we can bring to the CRT market. Recently, we had the Northeast Recycling Council conduct a CRT market survey for us, and I believe that some of the results of that will be discussed on a panel tomorrow afternoon. We also recently held a stakeholder meeting for federal and state environmental officials who run e-waste programs, as well as manufacturers and recyclers, and we did that in conjunction with ISRI and the ERCC this past May. And then, as I said, we've sponsored 2 CRT challenges with Innocentive to try and bring new market development ideas together. The first CRT challenge we did in 2011, and we had, I don't remember exactly how many entries we had that year, but we had 3 winners, 2 of whom are here today to talk about what they have done since winning their prizes and where their technologies stand in terms of development and deployment. Simon Greer is here from New Life Glass, and his solution is a very efficient heated furnace, and he produces glass products there, and he'll tell you more about that in a few moments. And then Mario Rosato had a closed loop process which separates the lead from the glass, and it has high market value for a variety of industries. Robert Kirby was another winner of the first challenge. He could not be with us today, but his idea was to combine CRT glass with cement, and he's creating tile and bricks that are tested, labeled, and sold for applications where lead shielding is used. Okay, and with that, I am going to introduce Mario Rosato, who is the founder of Sustainable Technologies. He is based in Barcelona. He is an engineer with 3 different engineering degrees, electric, electronic, and environmental engineering. And his technology that he'll tell you more about is in the laboratory stage still. He has one potential investor from New Zealand, and he's looking for others. His preliminary testing shows that thus far he's got more than 60% of a recovery rate with the first run of his testing, and we're excited to hear more from Mario. So welcome.
Thank you, Allison. So the process I will introduce to you is, as Allison said, still in laboratory stage. The challenge tends to solve this problem. You already know that the CRT cathodic ray tube glass contains about 30% of lead oxide. Lead oxide, must be said, is a material that can be found in 2 different states. So the problem addressed by the challenge was recovering the lead or the lead oxide in order that free the glass to be recycled with ordinary glass smelting facilities. Why cannot it be recycled with bottled glass, for instance? Is because of the high content of lead oxide, which is more or less soluble in water and could pass, for instance, to wine or beverages contained in the bottles. So in order to recycle that glass, we need first to extract the lead. The challenge did not specify whether to extract it in the form of oxide or in the form of metallic lead. Another of the problems for recycling this kind of material is that it is a short-term investment. Why? We will see that there will not be much leaded glass to recycle beyond 2030. So any process that can be a winning alternative for the market must be designed in order to have a very low investment cost and a very short return time. And furthermore, the solution had to avoid any spills to the environment. I must say that in your specifications, you did not include any parameter on CO2 emissions. For my company, this is a crucial argument. So in my solution, I stated as my own personal goal also designing a process with the lowest possible CO2 emissions. Okay, so you see written in red a parameter of the process which was not asked explicitly by the challenge, but I inserted myself. So let's see how the solution works. Since I decided myself that I had to keep the CO2 emissions low, I discarded any process that requires smelting in order to recover the lead. Why? Because I assumed that the glass will be smelted in a second phase. So using temperature, that is energy, to recycle the lead means emitting twice the CO2 to the atmosphere. So I decanted myself for looking for a chemical way to extract the lead from the glass. And the idea came to me by visiting a museum in Italy, where I saw some glass bottles from the size of the Romans, which had a very strange color. And I asked myself why that glass had that particular color. And I found in a paper that old glass that has suffered leaching during 1,000 years or 2,000 years tends to lose some of the mineral components and assumes that strange color. So it came to me the idea to perfection a system based on the leaching principle, and at this point the goal was finding which was the chemical reaction necessary for separating the lead oxide or the lead from the glass. Furthermore, I decided that the process had to be batch in order to be a simple plant that can have a very low investment cost. And of course, it must have a low energy consumption, which is typical of leaching processes because they don't require, they only require mild conditions for working. That is normally ambient temperature and pressure, or in the worst of the cases, hot water or hot chemical medium. Okay. So the last thing was what kind of material to recover, either lead in metallic form or lead oxide. We must say that lead oxide can present itself in nature in two forms. Depending on how the material crystallizes, you get it red or yellow in color. It is chemically the same thing, but the color is given on the way that light is polarized, and it depends on the composition of the crystals. For our scope, it is there's no difference in the price of red or yellow lead oxide. Okay, so I didn't care about this aspect, and I just concentrated on the process itself. The process, as I told, is based on leaching a chemical solution on a batch bed of pulverized glass and precipitating in an external tank the lead oxide. I won't tell you which is the chemical because it is not yet patented, this process, so I am just explaining the general idea. It's a combination of acid and basic processes that works in a closed loop, and as a final result gives in the second reactor, the one you see lower, gives a precipitate of hydrated lead oxide that can be dehydrated at a not very high temperature, so requiring a small amount of energy. The interesting thing is that the solution that must be leached across the pulverized glass can work at a temperature that is not necessarily very high. It is an aqueous solution, so we cannot go beyond the boiling point. This interesting aspect gives as a result that we can potentially use solar energy for fueling at least the thermal part of the process. Of course, we will need energy for the pumps and for the pulverizer. That is not considered in this sketch of the process. Why I chose a batch process can be deduced from this graph, which was part of the challenge. It is a study, I think it was from the MIT, wasn't it? In which the researchers analyzed which is the demand of recycled glass and which is the collected amount of glass that is being stored because there is not enough demand. So you see that the historical series gives a tendency which is quite linear. If we linearly extrapolate, we find that by 2020, 2019, there will be no more demand of leaded glass for producing CRTs, and we will end up with a high amount of glass which has no other destiny. So I took an average value and calculated on that average value the part which belongs to the United States, which is 50,000 tons of CRT glass per year. That will be the average amount of glass to be recycled. So if we assume 10 or 20 units around the American territory, that means that the plant that has to recycle this material needs no more than 20 tons of capacity per day. So it's a very small plant. So the idea came to me of developing this process in such a way that it can be contained in a 40-feet container. So the plants should be movable plants with a very low investment cost. So with this in mind, the other important aspect to be considered is what kind of material we are going to extract from the glass. The challenge expressly asked for decontaminating the glass in order to recover money from selling the glass to the ordinary glass smelting industry. But when we make calculation, if we recover the lead oxide, since this material has a higher value than metallic lead, actually the true business is recovering the lead oxide, and the glass can be considered as a byproduct. So the economicity of this plant, at least theoretically, because I repeat, is still in laboratory stage, is relatively high. We could extract between $200 and $300 per ton of CRT glass by selling the glass and the lead oxide. The system does not need much labor because it's a chemical process, a batch process, so you need a guy to load the plant in the morning and to unload it in the evening, and that's all. Eventually two, one for loading and the other perhaps coming once a week, a technician to perform quality controls, but not more than that. And the energy requirements are quite low because we are working in mild conditions, that is at room pressure and at a temperature that can be obtained by solar energy, that is between 40 and 80 degrees centigrade, maximum the boiling point of water, that is our limit. The optimum temperature and granulometry of the pulverized glass must still be determined. It's still in the research phase. Okay, so this is the result of my first run. As you can see, to your left, the small smelting pot has the aspect of being vitrified. It is actually vitrified because I set the wrong temperature in my laboratory oven and it melted. So you see that it turns rather it tends to be litharge because it's of a yellow color. The greenish bottom, maybe there are some impurities because, of course, the glass has also a coating, and this coating is creating some kind of interference with the chemical process. What you see at your right is the precipitate, which is still hydrated. So that's why it has different colors. But both of them have the same content of lead oxide. Okay. So the current status of the project is that we are still in laboratory stage. Several scrap processors have contacted me from several countries which are potentially interested in the process, but only one of them was willing to invest in developing the idea, patenting it, and eventually manufacturing the plants for sale. Another interesting consequence of adopting a leachate based process is that by switching the chemical, we can use the same machinery, the same plant, to recover other kind of valuables. For instance, we noted that in the CRT glass, there are parts per million of lanthanide, like niobium and these rare earth materials that have a very high market value. So we are analyzing in the laboratory how we could recover also these kind of materials which have a very high market value. And of course, if there is anybody of you who is interested in joining the team as investor, you are welcome. So with that, I don't have any more to add to my presentation. I am sorry if you were expecting to find a very high-tech process, but it's very simple to work this solution, and that's why it's potentially interesting, because it is simple and it works. Thank you.
Thank you, Mario. Our next presenter is Simon Greer. He's the owner and founder of New Life Glass, originally founded in the UK, and has a new facility here in the US now in Dunkirk, New York. That's upstate New York, close to Buffalo. And welcome, Simon.
Thank you. I want to go a little bit over our history of where the testing that we've done, creating, going through several furnace designs and technologies to create our process over the years, and explain the current process, how that works, and then I'll show you a film of the furnace technology. Lasts about 3 or 4 minutes, means I don't have to speak. And then I'll tell you afterwards about some of the results from that process, and just want to cover a couple of little alternatives and just give you some news about the site in New York, which Allison just mentioned. Leaded glass is, as Mario said before, it's the same stuff as you get in a wine glass, and I think it's worth noting that I know most people know this information, but it's the rear section, the tube of a cathode ray tube that contains the lead, and it is exactly the same material as you get in a wine glass. And it's also worth pointing out that, please make no mistake about this, lead does leach from leaded glass. It leaches from the surface, and if you crush it and get it down into small particles, the surface area of that glass is massively increased. But just take it, and any liquid will leach leach lead from the surface of the glass. But probably something that's will make it accelerate is something acidic, like rainwater or wine. So the lead crystal wine glass, for example, putting drinks in a decanter the lead leaches out from the inside of that glass into the drink to quite remarkable levels. I think there was a study done on some brandy that had been sitting in a decanter for about 6 months, and the levels of lead were around about 20,000 parts per million. Just bear in mind the leach level for landfill is 5. So it does come out, and really make no mistake about it. I realised this a few years ago, well, a lot of years ago, it's about 19 years now, and I started working on just small pots of glass by heating it up and adding some chemicals, which is quite old technology. It's called a reducing process, and what happens is that the particles of lead bound into the glass with the silica and many other ingredients with oxygen. And if you create an environment where the oxygen can come away from the lead oxide, then you can create a free lead particle. So that was the thing I was trying to do. I started off with tiny little pots inside a little gas oven at a glassworks, and these pots, I finally got a result out of it, and it's around about the year 2000, where I managed to get a tiny little particle of lead to come out of the base of one of these pots. And it was at that point that we'd really hit the eureka moment of knowing what the chemistry needed to be, and from there we could make further progress. This is 2002, thinner, less grey hair, a lot more money than I have now. And this was a small gas furnace that we were dismantling to inspect after we'd run some processes through it, just to see whether we'd got the lead zinc come out and see if it was harboured within the walls of the furnace, which it was. But that made us move on, because it realised that that we'd have to start making some rather dramatic changes, things that glass makers would find horrible, but that was to lift the furnace in the air. The lead, excuse me, I realised that the lead was we'd managed to get the lead to go to the bottom of the furnace, but the idea of lifting it out other than from anywhere other than underneath was going to be impossible. So we lifted the whole thing in the air. Glass furnaces are always made on the floor, and so these ideas were, to ordinary glass people, was ridiculous. And then we moved on to, it was that 2005 or somewhere around about there, that we built a 2-ton per day furnace. This was to run continuously. So the hopper at the back of the furnace there is delivering glass with the chemicals that are going to reduce the oxygen out of the mix. They're all pre-mixed and are driven into the top of the furnace, which is into the top of the furnace. You'll see later in the video of the one that's running in London how that works. But it's continually layering cold glass on top of the other glass, and beneath that surface is just where the reaction starts to take place, and the lead's encapsulated. The lead that's becoming free from the glass is being encapsulated beneath what we call the cold top. The glass carries on through the furnace, and the lead remains in the bottom of the furnace, which is where we can remove it. The furnace, you'll notice there's no chimneys with it, it's because it's run electrically. And in the side of this little one that we have, this little rods and stuck into the side of the furnace, which is how we run power straight through the molten liquid. And it's the resistance of that liquid that creates the heat. So we're heating it from the inside out, and this gives us great efficiencies with heat loss. The habit was starting to get a bit bigger, and this is a machine we made in Manchester, in England, and you can see on this furnace that on the left-hand side there, that's the molten glass that's coming out of the furnace. This is the hopper feeding the glass in, and so it's going to go on a journey into the furnace here, through the top, work its way down, and then eventually come out there with the lead coming out from the base. This furnace in Manchester was, I suppose, it's furnace number 1. and it was our pre-production or pre-selling, and we made some schoolboy errors really on how we'd get the lead out. It was very difficult. We'd made some mistakes. We emptied it, remodeled it, tried some different methods out, and then finally worked out how we'd build the next one. And we did that. We did a lot of that work with a gentleman called Patrick Watts, who's the owner of a company called Sweet, which is near London. They're a recycling company, and they were. I've always been a great supporter of what we were doing. And so with him, we started to build his furnace. And this is the one that's near London. That was just going through the construction process, and this was done last year. We were looking for a hot date of glass pouring out of the furnace and lead coming out of the furnace of October the 14th. I think it was 2 o'clock, our original forecast. From 6 months prior we started the building, and we were 2 hours early. So it was pretty good. You can see that this is looking at it from the front end, and you can see that the molten glass coming out of it. We have 2 options to taking the glass out from both sides. In the film that I'm about to show you, it's coming out from the other side. And you'll see in the film I'm about to show you that you will see it's hard to see. It starts off with there's a pipe coming out of some crushed glass. It goes into a hopper, which is where the glass is mixed with the chemicals, and then goes into what you'll see is a long orange tube that starts to feed the glass into the furnace. You'll notice also when the film's on in a second that there's some flames that come from the top of the where the glass has been put in, the cold top. And this is where the oxygen is breaking away from the lead oxide, and it creates a small little flame. So if I'll just show you that, and we'll come back to it in a minute. I forgot to say beforehand, the glass in that film was falling into water where it's quenched, and that glass is then ready to be used as an aggregate product. There are many other products that we've developed and have in development, which is where they'd not be falling into water, and the molten glasses are something that would be modelling into new products. The lead that was coming out of the back end of the machine, which we saw Candice Elena was taking it in her hands, that we managed to pull out as cold, so we can avoid any vapour issues. And so that's the complete process, and there is nothing else to come out of it. So there's no waste at all, and nothing else to deal with. And it ends up with product on each end. So we're starting with waste going in through that delivery pipe, and then just product. So nothing else to consider. The analysis that we'd looked at from this, the metals that were coming out, we were looking at the glass that was coming out, looking at the metals that were in it, is that was gone from a 20% lead content down to less than 1. In the UK, content of lead was the important piece, but here in the United States, the information is more about TCLP. And we've had these tests done independently from other places around the world. We've done them ourselves on many occasions, but as you can see there, the leach levels on the glass products that we've made are around about 1.5 parts per million, and the limit in the United States is 5. So the mission accomplished there. But there's another test that we do on it, which is a much more realistic test, which is all to do with how much lead's realistically going to come out. And again, looking back at that limit of 5 milligrams per litre, or 5 parts per million, we had to do this test in parts per billion because it was just so small, it was so hard to detect any lead coming out from the glass product when we'd finished. So the output of our machine, of our furnace that we've created, There's the lead that comes out, which is just saleable straight away. But the other output is molten glass. And this is something that we often have to sort of remind people. It's not the stuff that's been turned into sand through quenching in water. It's molten glass. So from that we can attach many machines to turn it into products. And as we move on, we will turn those into products which will always be of higher value. At the moment, the product ends up in bags, like you can see there. It's ended up all of the glass from the furnace in Manchester and the one that's in London have ended up in aggregate products. I was going to talk about the alternatives of where else glass can go, but I'm going to skip over this as quickly as possible. But just to say that, you know, we kind of regard ourselves in a bit of a third place here, because putting glass into a brand new TV, I think has got to be the most perfect recycling going. Take an old product, make something completely new with it, and it's perfect recycling. However, CRTs are not going to last, so it's not a sustainable solution. How long it lasts, I don't know. Mario put some figures up before, but realistically, the people who could answer that would be the people from Videocon. Then there's lead smelting. Lead smelting, again, they have to use the glass in their process as a flux to drive out the impurities in the lead. So what a great thing to do is to put leaded glass in and actually add to the lead that they'll extract from it. But again, it's not a massive requirement, so it can't handle all of the glass that's going to be available. And then there's landfill. Well, I'm not going to talk about landfill. I think everybody here is in agreement that it's just not a solution, and neither is storage. You know, there's a load of questions there. I'm not going to go through them. You know the answers to them. But the news I wanted to share with you today was to say that we've opened a facility in Dunkirk, New York. The reason it's at Dunkirk is because it's in the capture area for being able to get power from Niagara Falls, which is green, it's carbon free, and most of all, it's cheap. We've managed to get a really good deal from them, which we want. That facility is now open. We bought the building quite some time back, and it took a lot of time to just go through the legal pieces of actually buying it. And then we had to go through the permitting things, which that time took a little bit of time. But the DEC in New York, the environment people in New York, have helped us every step of the way. And as much as it's like trying to run through treacle most of the time, they have held our hand and they've helped us through it, and they've been very accommodating on helping us do what we do. In that building, it's currently, well, it's almost empty at the moment. There's some glasses gone in there, but not a great deal yet. We'll be putting a furnace in that building over the coming months. It's the one in Manchester we're going to be remodelling. It's going to be dismantled and moved here. And from there we're going to, and we'll be building a stockpile of glass. The life cycle of the furnace is going to be about 10 years, and it will melt 10 tonnes a day, which means that in its lifetime it will be melting 36,000 tonnes of glass, or to put it in pounds, that's going to be somewhere like 70 million pounds of glass, leaded glass, that it will process. If that glass comes in whole tubes, that means that building is going to have a capacity of 200 million pounds of CRT glass, and that's what that facility is set up for. We have the power at the site to put a second furnace in, so if there is more glass than that, we can double up, and we're happy to move to more sites around the country to be able to deliver a local service, so long as there's the glass to feed it. Those are just the things I was talking about now. So that brings me to the end of it. Thank you very much for listening, and thanks very much for coming to hear us today.
Thank you, Simon. Okay. We had planned today to have, if possible, the two winners of the 2013 CRT Challenge here with us. to present their ideas, but unfortunately neither were able to come. One is on international travel, and the other one had other business engagements as well. So I'm going to do my very best to present their ideas. The second challenge we sponsored this year, we extended the period. The first challenge we did with EDF, we did just a 30-day period for solutions to come in. And this time we thought, let's extend it to 90 days and see if we can get ideas that are a little bit more fleshed out and provide the solvers additional time. We received more than 100 entries. They're all submitted anonymously, so our technical review committee, which is comprised of CEA members, ISRI members, someone from NCER, and a state e-waste official, we didn't know whose work we were looking at to try and be as unbiased as possible. The criteria that we used, we said you had to use current material as it's currently produced, that the proposed use should be economically viable for recyclers, and we did not require the solvers to submit any sort of detailed budget with the proposal. We asked the solvers to propose uses that could ideally be able to be implemented within about a 12 to 18 month time span. And we also said that the solvers could identify sources of glass similar to CRT glass that could extend the time period over which the recyclers could sell the material, that would make the process even more economically viable. We also gave additional consideration to ideas where the government might be the end customer. And lastly, we said that the proposed use needed to take into consideration existing environmental regulations, and use of the lead-containing glass could not result in any emissions of significant amounts of lead into the environment, meaning the air, water, or land. So, our winners this year both focused on the vitrification of nuclear waste using CRT glass. Our winner was Dr. Thomas Engelhardt. He is a senior executive advisor to a major international investment fund, but he has a PhD in physical chemistry, and he won a $10,000 award. And our runner-up was Dr. Mariano Velez, and he is based in Missouri. He is a senior research engineer at MOSI, which actually is a glass company. And he has a PhD in ceramic engineering, and he won a $5,000 award. So here are a few slides from them on their different proposals. As I mentioned, Dr. Engelhardt, he holds a PhD in physical chemistry from the University of Würzburg, Germany. He's currently based in North Carolina. He began his career in chemistry with Ciba Geigy as a process development chemist in 1987. And he served in various executive management capacities for Ciba until its acquisition by BASF. And he also worked as Chief Technology Officer for the China National Blue Star Corporation, which is a major Chinese chemical corporation based in Beijing. His solution aims at using CRT recycled glass as a component in the glass frit used for the vitrification of nuclear waste. Basically, his premise was that vitrification of nuclear waste is attractive because of its flexibility, the large number of elements which can be incorporated into the glass, its high durability, and the reduced volume of the resulting waste form. This mature technology has been used for high-level nuclear waste immobilization for more than 40 years in France, Germany, Belgium, Russia, Japan, and the US. It involves melting of waste materials with glass-forming additives so that the final vitreous product incorporates the waste material in its micro and macro structure. Although initially developed for high-level nuclear waste, vitrification is being currently used for immobilization of immediate and low-level radioactive waste, such as from operational and decommissioning of nuclear power plants. Plans are currently in place to vitrify vast volumes of waste here in the U.S., and the world's largest vitrification plant is now under construction at Hanford in Washington State. When that plant becomes operational, it's estimated to go online in 2019 if it gets done on time. It's expected to produce over 160,000 cubic meters of glass. And the Department of Energy plans to vitrify 54 million gallons of radioactive waste at Hanford, which is approximately 60% of U.S. radioactive waste. The Hanford Waste Treatment Plant represents a long-term outlet for CRT glass, since operations are planned to run until 2028. So Dr. Engelhardt also said that in terms of potential benefits, you've got both nuclear waste treatment here. You could also use this to immobilize industrial hazardous waste. So that would open up other potential markets for the use. And in closing on his slides, he said that the open questions that have yet to be looked at here, a lot have to do with risk management. We need to look and see what sort of maximum percentage of CRT glass and lead could be used in this type of vitrification, and testing would need to be done to look at the concentrations, to look at total volumes of CRT glass that could be brought in. And same thing as well, if it were applied to industrial waste treatment, you would need to look at licensing for operations and also leaching rates. So that concludes slides from Dr. Engelhardt. And I will move on to our runner-up. Came Dr. Mariano Velez, as I mentioned, is with MOSI Corporation in Rolla, Missouri. He received a PhD in ceramic engineering from MIT and has conducted glass research for over 30 years, focusing on glasses with very high chemical durability, glass-reinforced polymer composites, materials manufacturing, design and properties optimization, use of nanoparticles and nanofibers, and evaluation of recycled and waste materials. Dr. Velez proposed two different deliverables in his submission. One would be an extensive literature review that would look at all different elements of CRT waste-related glass, including a cost analysis, raw materials and transport, and its impact on the environment. And then the second approach, very similar to what Dr. Engelhardt proposed, was an approach for developing the property composition model for using CRT glass waste forms to treat nuclear waste by making chemical, durable borosilicate glasses that are geologically stable. These are some areas that MOSI has looked at in terms of treatment of wastes, and some of the rationale of why things haven't gone very far along. They're looking, though, they would like to look more into the mobilization of nuclear waste in the far right column, and they're looking at doing the modeling of property composition and compiling a database. And according to Dr. Velez, he says that there are already several published works on recycling CRT-related waste glass. For example, construction materials, silica replacement in glass making, ceramics, and lead smelting. But none, in his opinion, is economically feasible due to the low cost of silica sand, plus the potential lead fume generation during melting, and the high costs involved in the CRT glass collection, storage, and transportation, in addition to industrial restrictions for complying with local and government regulations. He says, additionally, recycling and disposing of CRT glass is an event that, although is critical today and in the next 10 years or so, it is not a continuous material source for manufacturing, and any commercial product for longer time periods. So Dr. Velez posits that the only option of making the CRT glass into a geologically stable glass that can be safely deposited in the ground. Given that the U.S. is encapsulating nuclear waste into borosilicate geologically stable waste glass forms, the CRT glass can be a component of such waste forms where the lead content may be advantageous due to its radiation shielding capacity, contributing to lower melting temperatures, and producing a homogeneous waste form of glass. The main work proposed here is to develop and provide a property composition model for using CRT glass waste forms as raw material for encapsulating nuclear waste by making borosilicate glasses with very high chemical durability. The main information, he says, is needed is accurate chemical analysis and statistical experimental design combined with commercial databases. So he says the main question here is, will the Department of Energy approve such an approach? And that's where CEA and ISRI possibly have a role to play in approaching government agencies and sort of proposing these ideas and see whether we can run with them further. He also says that some of the things that need to be considered here are costs, timing, and composition certifications and other legal restrictions. In terms of using the raw material for nuclear waste encapsulation, he proposes using a statistical experimental design to formulate compositions and monitoring. He might choose to use other raw materials, and he wants to go ahead and look at melt and cast and verify properties. And I think we've got 2 more slides from Dr. Velez. He says one thing that we do have to look at if we go forward with this type of proposal is you have to do a chemical analysis of the relative homogeneous stockpiles. That would definitely be needed for application, and that compiling the database of required properties for use, including melting temperature, thermal properties, would need to be done, both from the literature and from monitoring stockpiles. And that with that information, then you could move forward and report findings to the Department of Energy and to other CRT stakeholders. So Dr. Velez's final remarks are, can we go ahead and consider the CRT glass waste as raw material for nuclear waste encapsulation? Will DOE approve? I believe he has already worked on funding approaches from the Department of Energy for other types of vitrification, so we might be in good standing to move forward on this. And that MOSI Corporation itself can do chemical analysis, melt, cast, and trial compositions, property determination, and formulation for any proposed use of the CRT glass waste. I made it through that. As you can probably tell, I'm not a glass engineer, so I thank you all for your patience. What we will be doing going forward is working with both Dr. Engelhardt and Dr. Velez to try and develop some further understanding of their ideas and vet them with other CRT stakeholders, and also, as we said, go ahead and talk with our colleagues at the Environmental Protection Agency and the Department of Energy to see if there's interest in trying these approaches. So that ends the formal presentations, and we welcome your questions. I have one question so far for Mario. In your process, does the leaching rob the glass of materials necessary for reuse? In other words, what happens to the purged glass?
What happens to what?
To the purged glass. Okay, do you want to read it directly?
Actually, in the leaching process, I am envisaging the reactives react only with the lead oxide. So the glass remains a silicate. There is no variation in the glass composition apart of extracting the lead oxide. So it's a glass that can be suitable for mixing with any other kind of glass for recycling facilities. So there is no variation in that sense.
Okay. All right, the next question is for both Simon and Mario. What is your reaction to the process announced by Kusakowski, which simply encapsulates the lead?
May I start? So, I have a bit of perplexity about that because, first of all, by mixing radioactive material with glass powder, which is then melted and cast into a pot, statistically we don't have the absolute certainty that the radioactive material stays in the center of all the cast mass. And since the decay in radiation is a direct function of the path that the radiation itself makes across the mass of glass encapsulating it, imagine that you have a mass of glass with the material inside. The particles of radioactive material that are near the surface are actually only mobilized, but they are leaking radiation. They are only stopped by the stainless steel barrier. Myself, I would have proposed the glass encapsulation, but in another way. Imagine to make a hollow pot with glass, then put the radioactive material inside and then seal that pot with a melting glass thick stratus. So in that case, you will fully utilize the potential of leaded glass to absorb at least alpha and beta radiation. Gamma radiation, I'm not sure it will be able to absorb. I would guess it will absorb very little. But for sure, that kind of solution will be easier to promote than actually encapsulating everything in the mass of glass. At least that's my opinion of somebody who is not expert in nuclear technology. Okay.
Simon, do you care to comment on the reaction to the process announced by Kusakowski?
Yeah, I know that they've got a beneficial use determination, which I think has been granted by Illinois State, and so you know, they're entitled to do what they plan to do. My concern with it would be related to the problems that have come from stuff being landfilled before. Back in the 50s, there was a place not too far from us in New York, which was called the Love Canal, which was a dug canal that was it didn't work out. So the people who made that canal sold it to a company called Hooker Chemicals, who later became Occidental, and they filled it with 21,000 tons of hazardous waste, and then sold it afterwards in the 90s, I think it was about the 70s, the early 70s. They sold it to the town, who put a school on top of it, and then somebody with a digger back axe went through the sides of that landfill and burst it, and subsequently the Occidental were sued $127 million for not controlling the waste that they'd dumped, and thought they got away with it some years before. The relationship from that horrible affair to this one is that the daily cover of hazardous glass on a landfill site, which is going to get laid up like a good lasagna at some point in the future, we're going to want to remine these places for plastics or other materials that are going to be in them. And the moment somebody goes through that with a back axe or with a digger, they're going to be pulling up hazardous waste. Because as much as it's going to be encapsulated, I don't know how long is it going to last. I think the term in the press release was virtually. I think it was virtually leach-proof or something like that. It's just a concern. If it's it's leaded glass, you're putting leaded glass in a non-hazardous landfill site. It's hazardous landfill in the wrong place for me. But they can do it. It's legally, it's allowed.
Okay, I have another question for Simon. What is the purity level of the lead recovered in your process?
Generally 99%. The other 1% is made up of antimony, which is what a lead processor would expect to be there.
Okay. Another one for Simon. First, a comment. Thank you for bringing your technology to the U.S. from our commenter. And question. You mentioned that the facility in New York is open, but has a limited lifespan. How is New Life addressing upfront the closure of the facility at the end of its life, and what were the permitting considerations?
Closing of the furnace after its lifetime, I would expect that to be somewhere about 10 or 11 years. Will be that the last piece of glass will be gone. It'll be an empty building at the end of it. There'll be no glass left, just a furnace that will be dismantled and recycled. I'm sorry, what was the other part of the question?
I think that was it. Any other permitting considerations that had to be thought out, seeing that it's a short process?
Permitting, the initial part of the permitting sits under the ordinary Waste 360 permitting, which is to do with the CRT rule. And then as the furnace is being built, it goes under the V permit, which is a hazardous waste permitting. And as much as a lot of people get bothered about hazardous waste permitting because of the depths of it, but that's what we do, and we do that in the UK. That's normal business for us.
Okay. A question for both the presenters. Do you pre-process your own glass? And what size is needed for the leach reaction or melting?
Well, that's actually a question I cannot answer because the process is not yet patented, so it's sensitive information. Sorry.
Okay.
2 millimeters.
2 millimeters?
Yeah, we crush the glass down to size 2 millimeters. Bigger than that, we found that the chemicals that were going into the process took a little bit longer to get through to the centre of the mix. So when we first did it, we were pulling glass out that had a too high lead content, and we just gradually brought it down. It was through years of testing, just brought it down further and further, and so we got to a size of about 2 millimeters, which works really well.
Very good. And I have one last question here, unless there are any others floating around. Has vitrification been considered for any treatment of nuclear waste from the TEPCO facility in Japan, which was hit by the tsunami? As far as I know, vitrification has been potentially considered in Japan. I don't know where they're at with the status of that. They're still actively in very concentrated phases right now of cleanup. And so I know that it had been considered, but I don't know what the government or TEPCO has decided to do there, and if they were going to do any vitrification, would it be just from straight glass, or would they use glass that could potentially have additional radioactive shielding properties if it used lead? So that's my knowledge. I don't know if our other panelists have any further information on that. No? Okay. All right. Any further questions? I think we've got a few more minutes. Well, if there are no other questions, I'd like to thank you both again, and I'd also like to thank the conference organizers, my colleagues at CEA and at ISRI for working on the CRT challenge, and thank you to all the audience for coming and hearing us.